Hello statistics and welcome back to the video lecture series on the normal distribution. Today we are going to be using the normal distribution to find unknown values. So what this is going to involve is actually finding a z-score that corresponds to a given area under the standard normal curve. So what's going to happen here is sometimes you're going to be given a particular area, either the area to the left or the area to the right, and you want to find the z-score that has that cumulative area to the left. Now, there's a couple different ways to do this. The most accurate way to do this is to scan the standard normal table to find the area that you're looking for. If you can find most of the exact areas that you're looking for in the standard normal table, and you're going to then figure out what z-score corresponds to it by kind of working backwards. I'm also giving you another table called the inverse standard normal table. Now this inverse standard normal table is available on Canvas, and you're going to see a link to it right around the link for this video. And if you open it, you will notice that it is a lot smaller than the standard normal table, so it is not accurate. But what the inverse standard normal table is it is a table that gives some of the more common areas that you would feasibly be looking up and the z-score that goes with those areas. Now the thing is, it's some of the most common areas. That's why the table is so small, but these are the areas that you're going to be looking up the most often. However, if you cannot find the exact area that you're looking for in the inverse standard normal table, you do need to go to the regular standard normal table and find the exact area that you're looking for and find the z-score that goes with it. The inverse standard normal table can also kind of help you out and give you a guide of where in the standard normal table to look for the z-score that you're looking for. So the inverse standard normal table, I will go ahead and say, is going to be most useful when we get to percentiles, when we're going to find a z-score that goes with a particular percentile. So let's use the standard normal table first, and then we'll move into using the inverse standard normal table. So what we're going to do is we're going to use the standard normal table to find the z-score that corresponds to a cumulative area of 0.3632. Cumulative area means area to the left. So we're basically finding a z-score that has an area to the left of 0.3632. So we're going to go into the body of the standard normal table. We're going to be, looking in, these numbers here in the middle, and we're going to see if we can find 0.3632, which if you look, it is right there. The z-score that goes with it is negative 0.35. So the z-score that has a cumulative area of 0.3632 is negative 0.35. Then for number 2, we're going to find the z-score that has 10.75% of the distribution's area to its right. You might remember that I really said ad nauseum in the last video that this table only ever deals with area to the left. So all of these numbers that are in the body of the table are all areas to the left. So if you want the z-score that has 10.75% of the area to its right, that means the area to the right is 0.1075. The only thing that you will ever be looking up in any of these tables are areas to the left, whether that's the regular standard normal table or the inverse standard normal table. They only ever deal with area to the left. So the easiest way to find the area to the left is just 1 minus 0.1075, which is 0.8925. So what we're going to do is we're going to go into the standard normal table. We're going to go into the areas in the body of the table, and we're going to see if we can find 0.8925. So if you look right here, there we go. We see 0.8925. So since we found the exact area we're looking for, that's the z-score that we're looking for. So the z-score that goes with that cumulative area to the left is 1.24. Now, this can be a little bit of a pain in the neck, and it can be a little maddening sometimes, but it is the most accurate way to find the z-score that goes with an exact area that you're looking for. The inverse standard normal table that I've also provided you gives you some of the most common areas to the left that you would be looking up in application problems and the z-scores that goes with them. The inverse standard normal table gives you the z-score that goes with most percentiles. Remember, percentiles, we covered these in 2.5. Percentiles are the percentage of the data that comes before a given value. It's basically the cumulative frequency for a given value of x. It is the percentage of the data that is less than a given x value. Sound familiar? Percentiles are the area to the left of a given data entry. So in a normal distribution, percentiles are going to be the area to the left of a given value of x. So for example, if you're looking at a number in the 30th percentile, that means in the standard normal curve, 30% of the area underneath the standard normal curve is less than your value of x, which means that the area to the left of your given value of x is 0.30. Now what you can do is you can use the inverse standard normal table to find the z-score that corresponds with the given percentile. That's going to be the biggest use of these tables at this point. We are going to use them later in the course, but the inverse standard normal table will help give you the z-scores that go with really any percentile. So if you want to find the 30th percentile, if you want to find the z-score that goes with the 30th percentile, all you have to do is look up 0.30 in the inverse standard normal table. So if you look up the area to the left of 0.30, the z-score that goes with it is negative 0.524. So this is a snapshot of the inverse standard normal table, and what we're going to do is we are going to find the z-score that corresponds with each of these percentiles. Remember, percentiles are the percentage of the data that comes before a given value. So this is going to be the area to the left of our given z-score. So for example, percentile 5, that's what this stands for. P5 means look up the z-score that goes at the 5th percentile. Well, 5th percentile means that 5% of the area falls below our given z-score. 5% as a decimal is 0.05. So if you were to look up 0.05 in the inverse standard normal table, that will give you the z-score that has an area to the left of 0.05. So if you look up 0.05, you get a z-score of negative 1.645. And you can go ahead and use all of those decimal places that come after it. So then for number 2, we're looking at P50, which is the 50th percentile. So we're looking up the z-score that has 50% of the data to its left. 50% is 0.5 as a decimal, or 0.50. And you might be able to figure this out without even looking at the inverse standard normal table. This is in the exact middle. It has a z-score of 0. And if you do look up the area to the left of 0.50, there it is with a z-score of exactly 0. That means this is at the mean. So the 50th percentile is also known as the mean. So then for number 3, P90 means we are looking up the 90th percentile. That means that 90% of the distribution's area falls to the left of our given z-score. So 90% as a decimal is 0.90. So we're looking up the z-score that has an area to the left of 0.90. So we're going to look up under the area column, we're going to look up 0.90 and then find the z-score that goes with it, which is 1.282. So that is how to use the inverse standard normal table to look up the areas to the left, to look up the z-scores that go with the areas to the left of some very common areas like percentiles. Now, if you look, there's a lot more than just percentiles in these tables. Like I said, we're going to be using these tables for other contexts in later chapters, so don't get rid of either of these tables after we're done with this chapter and exam. We're going to be using these a lot in this course. So for now, we're going to basically be using them for percentiles and very common areas to the left. But remember, if you cannot find your exact area to the left in the inverse standard normal table, you need to go into the body of the regular standard normal table and find your z-score that way. Now, the whole point of doing this is to find the X value that goes with a given Z-score. So what we would do is if any of these percentiles were in some sort of real life context with a mean and a standard deviation, we would then turn these Z-scores back into a given data entry X that would then be applied back to the original context of the problem. So to transform a Z-score back into an X value for a given population, we are going to use this formula here. So X is going to be the mean plus Z times the standard deviation. This is actually your Z-score formula solved for X. So I'm just going to show you where this formula comes from really quick. If you were to solve this Z-score formula for X, first thing that you would do is you would multiply both sides by sigma. So you get Z sigma equals X minus the mean. Then you would add the mean to both sides to give you X equals the mean plus Z sigma. So it's really just the same Z-score formula, but solved for X. So this formula will turn a given Z-score back into an X value for a given population that has a given mean and standard deviation. So here's an example. Let's say a veterinarian records the weights of cats that are treated at a clinic. And the weights we know are normally distributed with a mean of 9 pounds and a standard deviation of 2 pounds. So our mean is 9 pounds and our standard deviation is 2. We're going to find the weights X that correspond to Z-scores of 1.96, negative 0.44, and 0. And then we're going to interpret these results back in the context of the problem. So let's start off with 1.96. So we're going to turn 1.96 back into a Z-score by using the Z-score 1.96 back into an X value by using the formula X equals mu plus Z sigma. So the X value that goes with the Z-score is going to be the mean, 9, plus the given Z-score, 1.96, times the standard deviation, which was 2. And we get an X value of 12.92. So that means that in this population, a cat with a Z-score of 1.96 weighs 12.92 pounds. So a 12.92 pound cat in this population would have a Z-score of 1.96. So then for the second one, we're going to do the same thing. So what I want you guys to do is I want you guys to pause the video and I want you guys to try this on your own. I want you guys to find the X value that goes with the Z-score of negative 0.44 and interpret it back in the context of the problem. Okay, so we're going to turn this Z-score back into an X value by using the formula X equals the mean, 9, plus the given Z-score, negative 0.44, times the standard deviation, 2. So then when you do you can just enter all this into a calculator all at once. You get 8.12. So in context, a cat that weighs 8.12 pounds will have a Z-score of negative 0.44. So then for the last one, we have a Z-score of 0, and you probably don't need to do any work for this, although you could. If you were to go through the formula, you would get an X value of 9. Because remember, if you have a Z-score of 0, that means that the data entry in question is exactly at the mean. So a cat with a Z-score of 0 would be a cat that weighs exactly 9 pounds. So a 9-pound cat would have a Z-score of 0, which is exactly average for this population. Here's another application of why you would turn Z-scores back into X values. So let's say that we have scores for a California peace officer's training test. Those scores are normally distributed. And those scores have a mean of 50 and a standard deviation of 10. An agency will only hire applications with scores that are in the top 10%. And what we're going to do is we're going to use that to figure out the lowest score that an applicant can earn and still be eligible to be hired by this particular agency. So what this means is that the scores themselves are normally distributed. It's got a mean of 50 and a standard deviation of 10. This particular agency is only going to accept applicants that have scores in the top 10%. Top 10% is an area to the right. So there is some sort of cutoff score. That cutoff score will have an area to the right of 10%. 10% as a decimal is an area to the right of 0.10. So what we're going to ultimately be doing is we are going to be finding this value of x, this score, that separates the top 10% from the rest of the scores. To do that, we need to go in stages. We need to first find the z-score that goes with this area, and then we're going to turn that z-score back into an x value to get the test score that will determine the top 10%. However, which area does either table always deal with? Either table always deals with area to the left. Top 10% is an area to the right. So do not look up 0.10. That would give you the bottom 10%. That's not what you're looking for. If you're looking for the top 10%, that means 90% of the area falls to the left, which means the area to the left is 0.90. So what we're going to do is, the first thing that we're going to do is we're going to find the z-score that goes with the area of 0.90. The only areas that you should ever be looking up are areas to the left. So if you find the z-score that goes with an area of 0.90, you're going to go into the inverse standard normal table first, look up 0.90, area to the left, and you'll get a z-score of 1.282. Second thing that we're going to do is we are going to turn our z-score back into an x value. To do that, we are going to use the formula x equals mu plus z sigma. So the x value that goes with this z-score is going to be the given mean for the population, which is 50, plus the z-score that we just found, 1.282, times the standard deviation for this population, which was 10. So then if you enter all this into a calculator all at once, you get 62.82. So what this means is that the cutoff score for the top 10% is 62.82. So 62.82 is the lowest score that an applicant can earn and still be eligible to be hired by this agency. So I want you guys to try that for this next one. I want you guys to pause the video, read through this problem, and it's going to be basically very similar, except this time we're looking at the bottom 1% instead of the top 10%. So I want you guys to give this one a try and find the x value that goes with the bottom 1% for this population. All right, so the mean for this population was 181 milligrams per deciliter, and the standard deviation was 37.6 milligrams per deciliter. This is just the units of measurement for cholesterol levels. So we're going to find the highest cholesterol level that a woman in this age group can have and still be in the bottom 1%. Bottom 1% is an area to the left. So I'm just going to draw a quick picture of what we're dealing with here. So we're looking for the highest cholesterol level that a woman can have and still be in the bottom 1%. Bottom 1% means the area to the left of this given cholesterol level is 1%. To turn 1% into a decimal, you divide by 100, so that means the area to the left of this given cholesterol level is 0.01. So the first thing that we need to do is we need to find the z-score that goes with this area to the left, and then we're going to turn that z-score back into an x value. So we're going to turn the z-score back into a cholesterol level. So since this is area to the left, we don't have to worry about doing any of that subtraction like we did for the last one. So you're just going to look up in the inverse standard normal table 0.01. So if you look up 0.01 in the inverse standard normal table, you get a z-score of negative 2.326. So that's the z-score that goes with the bottom 1%. To find the cholesterol level that goes with the bottom 1%, you need to turn your z-score back into an x value. So we're going to use the formula x equals mu plus z sigma. So the cholesterol level x is going to be the mean 181 plus the z-score we just found, negative 2.326, times the given standard deviation, 37.6. So then that will give you an x value of approximately 93.39. So a cholesterol level of 93.39 milligrams per deciliter is the highest cholesterol that a woman in this population can have and still be in the bottom 1%. So the cholesterol level that goes with the bottom 1% is 93.39. So then for this last one, it's going to be a very similar idea. So I want you guys, if you want to, you can pause the video real quick and then try this one, especially if you weren't comfortable trying the last one. So go ahead and pause the video and work through this one. We're looking at the bottom 10% this time. All right, so we have the salaries of elementary school teachers in a given district are normally distributed with a mean of $34,000 and a standard deviation of $2,000. What is the cutoff salaries for teachers in the bottom 10%? So bottom 10% would mean that the area to the left of a particular salary is 10%. So we are finding the cutoff salary that has an area to the left of 10%. So 10% of the teachers would have a salary below this cutoff salary. 10% as a decimal is 0.10. So the first thing that we need to do is we need to look up the z-score that goes with this given area to the left, and then we will eventually turn that z-score back into a salary x. So which area does the inverse standard normal table always deal with? It always deals with the area to the left. So what you're going to do, since this is the area to the left, you're going to look up 0.10 in the inverse standard normal table. That gives you a z-score of negative 1.282. So that is the z-score that goes with the bottom 10%. To turn that z-score back into a salary x, you're going to use the formula x equals mu plus z sigma. So the salary x is going to be the mean, $34,000, plus the z-score we just found, negative 1.282, times the standard deviation, which is 2,000. Then when you enter all that into a calculator, you should get a salary of approximately $31,436. So the cutoff salary for the bottom 10% is $31,436. That means 10% of the teachers have a salary below this in this population. All right, so that is how to use the normal distribution and the normal table and the inverse standard normal table to find values that go with given areas. In the next video, we're going to be covering one of the most important theorems in this course, which is called the central limit theorem, and that will be the basis for a lot of inferential statistics that we will do throughout the course. So stay tuned for that. Thank you all very much for watching, and I will see you in the next video. Bye-bye.